Could somebody just say, are you seeing the video? Are you seeing my screen, I mean?
Yeah.
Good. All right, here we go. So number 1B, excuse me, number 1B, we are just going to simply cross this one out. You get asymptotes that are imaginary, which I screwed that up, so we are not doing that one, but we'll start with number 1A. So our goal is to start to connect these points of discontinuity with the domain. And in this problem, we're also going to look at x and y intercepts, but I'm also going to talk a little bit about the asymptotes as far as whether they're removable, non-removable, as we start looking at these problems. So what you're going to want to get used to doing every time we look at one of these rational expressions, and you'll see it in section 8.4 and section 8.5, is you want to factor everything. So that's what we'll start with. Your numerator, you've got a 2x squared plus 5. I checked the numbers 2 and 5. They have nothing in common that you can factor out. X squared does not have any partner x with this 5 that you can factor out. So this is not able to factor. So this just stays as 2x squared plus 5. Then we'll take a look at our denominator. Our denominator, you have an x squared minus 2x. There's no numbers I can factor out, but there is a common x. They both have an x in common, so I will factor out this x. X comes out. Then we're left with an x minus 2. So some of these polynomials I'll be able to factor out a GCF. Sometimes I'll factor a difference of squares, but this one you're just looking, they both have an x in common, so I can factor that out. Then the next thing we want to look at is for these points of discontinuity, and they're always going to be down in the denominator. So I'm going to check which values for my denominator, which values for x would make my denominator 0, which is simply just taking your factors and setting them equal to 0. So x equals 0, and then x minus 2 equals 0. So that tells me that my points of discontinuity are 0, because I'm just, again, looking for anything that makes my denominator 0. And then this one we can just solve in our head. 2 minus 2 would be 0, so another point of discontinuity is 2. Okay. We're going to jump right to the domain. So I did do the points of discontinuity first, because the points of discontinuity do determine exactly what your domain is. So my domain is going to be my x values. So x values that work in my function are all reals, except for the ones that make my denominator 0, which are the ones I just talked about, are the points of discontinuity. So my domain would be all reals, except for 0 and 2. So far we've answered the first part of the problem, find the domain and the points of discontinuity. And then the x and y intercepts, we'll do that here in a second, and determine whether the discontinuities are removable or non-removable. And this problem to start out is not the best because we don't really see a lot happening. But what you would check for is in your numerator and denominator, if you have any factors that are exactly the same. Like if I had a single x up here, I could remove that with this x down here. Because if you have the same thing in your numerator and denominator of a fraction, we've learned that they divide out, you can remove those. Also, I'd look for an x minus 2. Since I don't have anything that removes this x down here or this x minus 2, both of my points of discontinuity are non-removable. So 0 and 2 are non-removable. So both of those factors do not simplify with anything in the numerator, so those would be considered non-removable. And here's where I'm just going to kind of jump ahead to what we're going to be talking about in the next problem. That means that those are both going to be vertical asymptotes. So anytime we have non-removable factors, they're going to form vertical asymptotes on your graph. And we'll see that here in just a second when I head to graph this. So to find your x and y intercept, I'm going to graph it out and then start looking at my calculator to find my graphs. Oh, okay, then let's start putting this one in. So we'll make a fraction. So the online calculator has this feature. Most of your calculators have this. You can make a fraction. Up in our numerator, we'll put 2x squared plus 5. Denominator, we'll put x squared minus 2. X. So let me just double check that. That looks good. So we are going to look for the x and y intercepts, but I'm also going to show you that you can see those asymptotes as well. So there's our graph. So on your graph, we're only seeing this 10 by 10, but a couple things we can start to see is this x equals 0. You can see your graph's approaching that. X equals 2, you can see this hyperbola kind of going to reach it, and then this curve down here is going towards that x equals 2. So there's your two asymptotes. You can also see your points of discontinuity in your table. So if you head to your table, at 0, we can see there's an error. That's how your calculator tells you that that's a point of discontinuity. At 2, there's an error. There's another point of discontinuity. And since both of those did not remove, they're non-removable, that means they're both asymptotes. We'll see on number, I think it's D, we'll see some that are removable. Okay. As far as the x and y intercepts go then, well, since there's an asymptote at x equals 0 right here, there is no y-intercept. And kind of going ahead again, and you guys did this on your class check, and you guys all did awesome, was that anytime your degree is the same in the numerator denominator, you're going to have a horizontal asymptote at the ratio between the leading coefficients. So there's an asymptote at 2 right here, which is causing your graph not to be able to reach the x-axis. So kind of lame here, but your x-intercept is going to be none, and your y-intercept is going to be none. So both of those, all those curves on your graph are never going to touch the x-axis. They're never going to touch the y-axis. So that would be problem 1 in its entirety. So we started actually finding the points of discontinuity. That tells us what our domain is, and then we can graph out to find those x and y intercepts. You could also do the x and y intercept just knowing how asymptotes work. So we know that 0 is an asymptote, so that means the y-axis is never going to be touched. And since your degrees are the same, you have that horizontal asymptote at 2, which means that your x-axis also will never be touched. So we're skipping B, we'll head down to look at C. So just like we did before, we are going to factor everything before we get started. So there's a common 3 in both of those terms, so 3 times x minus 1. And we have an x squared minus 1, which is a difference of squares, so we'll have an x plus 1 and an x minus 1. And we'll start by finding our points of discontinuity. So we'll take each of those denominator factors, set them equal to 0 to find out which x values make our denominator equal to 0. So once we get it factored, we can set each factor equal to 0. So our points of discontinuity are x is equal to 1 and -1. And you could put those in either order. That's fine. So x equals 1, -1, those are our 2 points of discontinuity. So in the function, if you put a -1 or a 1 in, it's not going to work at that point. That's your point of discontinuity. Now the points of discontinuity are also going to determine my domain. So domain is all reals, x cannot equal 1 or -1. So that point of discontinuity will start to tell us exactly the domain as well. That's the connection. Now we check to determine whether these points of discontinuity are removable or non-removable. So I'm seeing we have an x minus 1 up here. If I have the exact same factor, x minus 1, that means that this factor's point of discontinuity is a removable, which in turn does mean that it is going to be a whole. So we are going to say that 1 is removable. I'm just going to abbreviate that, REM, and then I'm just going to put in parentheses that does mean that it makes a hole at that point. And when we graph this, we'll see that hole forming. And then -1, so this x plus 1, this point of discontinuity, -1, does not remove, so -1 is non-removable. So you're just simply looking at, does the factor simplify with something in the numerator that's its exact same factor? If it does, that removes, it's a whole. Non-removable, like we found above there, that's going to mean it's a vertical asymptote. All right, we'll continue then. We'll look at the x and y intercept. One thing I'm noticing right away, if you look at your degree, the degree of your numerator is 1. The degree of your denominator is 2. So whenever your degree in your numerator is less than the denominator, this is going to mean you have a horizontal asymptote at y equals 0. So you can think to yourself, if you have a horizontal asymptote at y equals 0, is it ever going to touch the x-axis? No, it's not. But we'll show it on the graph as well. We'll see that happening. And then we'll check to see if there is a y-intercept. So we'll head back to our graph. Up in our numerator, we had 3x minus 3. Denominator, we had x squared minus 1. And head to our graph. So you're seeing this is your y equals 0. There's your asymptote because your degree in your numerator was less than the denominator. And you're seeing here this non-removable factor, that x plus 1 that did not remove, is forming this asymptote at -1 right there. To find your y-intercept, you can see that it does cross the y-axis here because there is no x equals 0 asymptote. Just head to your table and look wherever whenever x is equal to 0, that's where your y-intercept is. So here, our y-intercept is just 3. And there's your points of discontinuity again. So x can't equal 1 or -1. So there would be your points of discontinuity. All right, so x-intercept we said was none. There's a y equals 0 asymptote. And y-intercept is 0, 3. And there we go. So that would be it for number 1C. Okay. Heading over to D. So I'm realizing when I'm sharing my screen, I'm not able to see any of your chats. So if you do need me to stop, just turn on your microphone. You can tell me to stop, interrupt me at any time. No problem. And if you do need to leave, remember I am recording this, so I will post it to Schoology later if you want to go back to check it out. But let's go do that last one because we are on a roll here. Let's check it out. So here we've got a 6 and a 3. So we're just kind of looking at the numbers. Yep, they both have a 3 in common. So we'll go a 3. And then we've got a 2 minus x there. And if we look at our denominator, we've got an x squared minus 5x plus 6. So a trinomial is going to factor into 2 binomials. We're just asking what's going to multiply to +6 and then add to -5. That would be x minus 3, x minus 2. So that will tell us our points of discontinuity. And don't worry about removing things yet. We'll get to that in a second here. We're just going to find those points of discontinuity. So I'm going to kind of skip the last step where I set them equal to 0. Hopefully you're kind of picking up on that. This is just going to be a point of discontinuity at 3. This one, put a 2 in there. That's going to make it 0. There's your point of discontinuity at 2. That also will tell us domain. X can't equal 3 or 2. So there's going to be our domain. After that, we got to start checking to see if anything removes. And I'm really focused on this 2 minus x, x minus 2. They do look very similar, but they are not in fact the same, so we can't remove them yet. So the problem is that this 2 is positive, this 2 is negative, this x is negative, this x is positive. But think about, how could I multiply or divide? I'm going to say divide. How could I divide 2 by something to make it negative? And how could I divide negative x by the exact same thing and make it positive? Well, if we take and factor out a -1 out of both of these, they're going to change their signs to the opposite. So I'm going to factor out a -1, which comes out, multiplies this 3, becomes -3. And the the negative x, now that factors -1 out of it, it turns to positive. And when I divide 2 by -1, that makes it negative. So when I factor out a -1 out of both of those terms, it changes them to their opposite sign. Down here, I had the x minus 3, x minus 2. Looking now, I've got something that's removable. X minus 2 removes, x minus 2 removes. So there's my removable, which removable will make a whole. So we're going to have a x equals 2 that is removable, which makes it a whole. And I forgot to mention on the graph on the last one, your calculator won't like show a whole, like an open dot, but you will see it in your table that it'll say error. And then when you look, you'll see the consistent curve. But when you're graphing a hole, you're just going to put an open dot at where that position is to show that there's a hole there. There's no solution at that point. But there's your removable, there's your hole. And then non-removable, we had x equals 3, which we know now that anytime it's non-removable, that will form that vertical asymptote. So there's our results for our point of discontinuity. We'll head back to the calculator, we'll graph it, and we'll see all this stuff happening. And this time I'll show you kind of a little bit more about the whole. At x equals 2, we won't see it on the graph, but in the table you'll see that point of discontinuity. So find my calculator. So up in the numerator, we'll get our 6 minus 3x. I'm also looking at this again. The degree in the numerator is less than the degree in the denominator. So start thinking about, where is the horizontal asymptote on this one going to be? And it's always the same. There's no, it's just black and white. If the degree is less in the numerator than the denominator, you're always going to have an asymptote at y equals 0, no matter what. Okay, there we go. And just double checking, looks good. So there's our y equals 0. We're seeing that form. And our non-removable, x minus 3, is forming that vertical asymptote. So 2 was the other point of discontinuity. We're not seeing a hole at this position, but if you head to your graph, your table, you will see there's your hole right there. So the asymptote, you can see your calculator just kind of shows those curves approaching the asymptote. I would like to see, when you guys graph them, you just put the dashed lines so you can kind of identify where those asymptotes are, and then graph your curve towards it. The point of discontinuity 2 is the hole, and it's not on the graph, but we can tell that it's a point in discontinuity based on this table. So there would be number 1, A, C, and D. So we'll head back to that. Just want to zoom out for those that are going to watch the video later. So there's all our work. Oh, let's add in, forgot to add in those intercepts. So x-intercept was none because of the y equals 0. Make sure we identify that. And y-intercept was 1. So found that looking at the table, wherever x is 0, that's your y-intercept. That'll be where you can find that. So that would be number 1. There it is. All right, I'm going to save this, and then we'll head into number 2. So we've already been doing this, finding these vertical asymptotes, and it's all about finding the points, or excuse me, finding the factors, and then finding whether or not they remove. And if they remove, then you have a hole. If they don't remove, then that means you have a vertical asymptote. So this first one, this one's kind of nice. I've got just a plain 3 up here. I've got an x plus 2 down here. So x plus 2 is going to form my point of discontinuity. So I got x plus 2 cannot equal to 0. So we'll set that up. That means x equals -2. There's my point of discontinuity. Now, is it a vertical asymptote or is it a hole? Since x plus 2 has no factor of x plus 2 to remove it from the numerator, this is non-removable, which I'm just going to say this one is a vertical asymptote. If you want to graph that one on your own to see it, you can. I am not going to graph that because we did a bunch of graphing on that last one. But that's what you will see. First one, x equals -2 is a vertical asymptote. Part B, we've got an x plus 3 up here. We've got a 2x plus 3x minus 1 in our denominator. So we'll find our points of discontinuity. 2x plus 3 equals 0. To solve this, we'll subtract 3 over. We'll divide by 2. That means x is going to be -3 over 2. And x minus 1 equals 0. That one we can just solve in our head. X equals 1. So there's your 2 points of discontinuity. Then you're checking again. Do they remove? Nope. So this one is going to be a vertical asymptote, which I'm going to abbreviate as VA. And this one, vertical asymptote. Both of those will be vertical asymptotes. On to part C. In our numerator, we've got an x squared minus 4, x plus 2. We'll see a lot of these whenever you have 2 terms in a subtraction, and then this you're looking for if it's a perfect square, which 4 is. The square root of 4 is 2. That's a difference of squares, which is going to factor into x plus 2, x minus 2. So we'll get this factored. Remember, always start by getting them factored. The first 2, they were already factored out for us, which was nice. We didn't have to do this step, but you're always going to need to do this step first. Just get everything laid out, all the factors ready, and then start attacking it. So x plus 2 is in our denominator, so we'll find that the point of discontinuity is x equals -2. And now we start to look, is there anything that it removes with in the numerator? And once we factored out that difference of squares, now we've got that other factor of x plus 2. There it is. So since it removes, this one is going to be a hole. If you weren't sure about that, you could graph this function out. You would see in your table that there would be a point of discontinuity at -2, but you would not see a vertical asymptote. This one actually would just graph this shape. It would just graph the y equals x minus 2. It'd have a slope of 1, y-intercept of -2. So you just see a straight line, but you would see that there is a point of discontinuity at -2, which is your hole. So there is problem 2. I think that's all we had to do. We had to find the vertical asymptotes and holes. We didn't have any that had both. We just had one or the other, but there would be our results for number 2. Okay, and heading into part 3, find the horizontal asymptote of each function. So we've been talking about this a little bit as we've gone through. This is very simply just looking at the polynomial in your numerator and your denominator and checking out the degrees and how those degrees compare. So that we have a reference. I don't really have a ton of room. Just off to the side here, I'm just going to put the 3 scenarios. So 3 things can happen. Let me zoom in a little bit. So number one, the first thing that can happen is the degree in your numerator. I'm going to call just degree m, so that's just your highest power in your numerator. And then your denominator, I'm going to call degree n. So first, if m is less than n, that means automatically you have an asymptote at y equals 0. Done. That's all you got to check. Degree, numerator, denominator, check to see if it's less in the numerator. That means that you have an asymptote at y equals 0. I'm not going to write this out again, but if you have your m is greater than n, that's going to mean that you have no horizontal asymptote. Okay, and the third thing that could happen is your degrees could be the same. M could equal n. That means that you're going to have a horizontal asymptote at the ratio of your leading coefficient. I'm just going to call my lead coefficient of m over my lead coefficient of n. And like I said, on the class checks, you guys all did very well with that. So you're getting the idea of when you're looking for horizontal asymptotes, you're simply just looking at the polynomial degrees. Once you find the degrees of those polynomials, then you can start to determine what type of horizontal asymptotes they're going to have. So in each problem, we're just going to look at the degree of the polynomials. This one, constant, so this one's going to have a degree 0. This one has an x to the first power, so this one's going to be degree 1. Okay, so 0 over 1, that means my numerator is less than. That's going to determine that I have an asymptote at y equals 0. So there's my horizontal asymptote. Part B, we'll take a look at the degree in your numerator is 1. Degree in your denominator is 1. Here, your degree is the same, so that means I'm going to take those leading coefficients. So I'm taking the highest degree, looking, okay, there's a 1 there. Highest degree, putting a 1 there. So that means my asymptote is going to be at y equals 1 over 1, or just y equals 1. So if you graph that one out, you'll see a horizontal asymptote at y equals 1. You'll also see a vertical asymptote at -5. So going back to what we talked about, x plus 5, point of discontinuity, -5. And there's your vertical asymptote. Last problem, we've got a degree in the numerator of 3. Degree in your denominator of 5. Oh, having some mouse problems here. Well, we'll just have to. Oh well. So we got a degree that's less in the numerator than the denominator. Again, that's just going to mean that we have a y equals 0. Okay. Let's see here. There, my mouse doesn't want to work very well. So y equals 0, degree is less in the numerator than the denominator. We're not worried about any of the vertical asymptotes on any of these, but like part B, since it's nice and factored out, there's a vertical asymptote at -5. Here, you had a vertical asymptote at -6. Do you have your other mouse? My mouse isn't clicking very well. Are you using it? Are you using it? Oh, okay. Well, I'll just see if this one keeps working or not. Okay, I'll zoom that out so on the video we can all see it. So we didn't have one that was no asymptote. that would have been if the degree was higher in the numerator than the denominator, then there would be no horizontal asymptote. All right, we'll head into the last section of problems, which is graphing. So we'll take a look at that next. Let me just save this. And so graphing, you're going to want to have your graphing calculator handy for these. So we'll zoom in on one of those here first. So this is kind of putting everything together that we've talked about. So we've talked about points of discontinuity. So we're going to find that after we factor. We'll factor everything first. Then we start heading into looking at the removable, non-removable asymptotes. And then lastly, we'll look if there are any horizontal asymptotes, and we'll start drawing those in. But we'll always start with factoring. So we'll get that set up here first. Up in my numerator, I've got an x squared minus 4, so another difference of squares, which is going to be x minus 2 and x plus 2. Denominator, I see a 3 and a 6, so they both have a 3 in common, so this would be a 3 and x minus 2. So something interesting happens here. We do see that we have a removable point of discontinuity, so I will have a point of discontinuity at this 2 right here, and I can remove that, so I'll do that. But I'm not going to have any asymptotes, any horizontal, or excuse me, vertical asymptotes, because there's no other factors down here, so I just have one thing that removes. And then whatever's left, I'm going to rewrite that. Y equals x plus 2 all right, this isn't working very well. X plus 2 over 3. Sorry about that. And there it is. So looking at what's left, so here's how these rational expressions, these rational functions will be graphed, is that once everything is removed from the function, they're going to take the shape of whatever's left. So thinking about all the functions we've talked about this year, this one is the function that has a degree of 1. So what type of shape do functions with a degree of 1 take? And if you are saying a line, you are correct. So this would simplify to this. Y equals x divided by 3 is like 1/3 x. Remember, this is a heart, so I'm tearing it apart right now. Plus 2/3. So we will see the shape of these graphs will take whatever their simplified version is. So x plus 2 over 3 is what it simplifies to. So it's going to take that shape of 1/3 x plus 2/3. Now, as we're getting started with looking at these rational functions, I still would recommend that you graph it just to kind of see what it looks like as well. So let's graph this thing out here. So x squared minus 4 up there. And 3x minus 6. And one thing I just kind of looked at whether or not they're vertical asymptotes. But we're seeing now, since the degree in the numerator is more than the degree in the denominator, there is not any horizontal asymptotes either. And because it does take that shape of a linear, that's kind of showing that as well. All right, let's graph it out. So there it is. So we can see the 1/3 slope happening. It's crossing my y-axis at 2/3. If we head to our table, we'll see our one little error there. So at 2, we do not have an output. So to find that point on our graph, I'm going to put 2 into my function. So this y equals 1/3 x plus 2. I'm going to put 2 in. I know that because it's a point of discontinuity, it doesn't work in the function. But I'm going to put a 2 in to see what its output is so I can put that hole. So I put a 2 in. I'm going to get y equals 2 plus 2 over 3, which is y equals 4/3. So this is going to be tough for me to do with this mouse, but 2 4/3 is going to be roughly right there. So it's like 1 1/3. So there's your hole. My y-intercept is right here at 2/3. And then I can just do my slope of 1/3. So I rise 1, run 3. So there'd be another point, rise 1, run 3. There'd be another point. So here's kind of my shape of my graph happening. If you want to just go back to your calculator and pick out a couple of points, you can do that as well. But there would be the shape of that graph forming. So just signify there's that hole. That hole's happening right there. And then the graph is taking the shape of whatever the simplified version of that function is. And this one, since it was y equals, mx plus b form, it's pretty easy to graph it. Otherwise, like when we get to this one, when we start getting these rational functions that are a little bit more complex, you can just head to your table, find a couple of points, and just sketch the graph. I mean, that's all we're really asking you to do is just kind of sketch it, find out where those asymptotes are, holes, if there's any holes, and then sketch kind of what the curve looks like. Well, let's head over to B. All right, B is already factored out for us. Whew, that'll be nice. Check, is there anything that removes? No. So that means that we're going to have an asymptote. I'll just put that here. X equals 4 is going to be my vertical asymptote. There it is. No holes, nothing removes. So let's graph that vertical asymptote. 1, 2, 3, 4. There's my vertical asymptote. Then we check horizontal asymptote. Well, degree in the numerator is 1. I'm just going to put D1 over another degree of 1. If both degrees are the same, that means my horizontal asymptote is y equals. My leading coefficient here is a 1. Leading coefficient here is a 1. So y equals 1 over 1, which is just y equals 1. So we'll graph the horizontal asymptote of y equals 1. So get those graphed out first. Then you can head to your calculator. And I'll head back to that if you missed it. So it'll just be a second here. Head up to our numerator. We had x plus 4. Denominator x minus 4. And we'll see, hopefully, that asymptote at y equals 1, asymptote at x equals 4, and there you're kind of seeing those form there. So there's your there's your y equals 1 happening, your x equals 4 happening, heading down here. And I'll look at my table, but really, guys, just kind of sketch where it's going. It's just a sketch. I'm more worried about your asymptotes. Can you find those and sketch out the graph? So let's just sketch it out. So I believe it came kind of down here like this, and then we're going to follow this asymptote. There's my sketch there, and this one follows my asymptote. It's heading that direction. So your vertical asymptote at x equals 4, your horizontal asymptote is at y equals 1. So that was nice. That one was factored out for us. Didn't have to do any of that. Hey, next one is too. So looking at this next one, x plus 6 up in my numerator, I look at my denominator. There's nothing to remove, so both of these are going to be vertical asymptotes. So we'll just make a list here. We got a vertical asymptote at x equals 2. That's because I'm just doing a point of discontinuity. So point of discontinuity, x minus 2 equals 0. So 2 minus 2 is 0. X plus 3 would make a point of discontinuity at negative 3. So those are both my vertical asymptotes. So we'll do x equals 2 right here. Graph it, x equals negative 3 right here. And there we go. So there's my vertical asymptotes. Next thing, I'll look for my horizontal asymptotes. So here I've got a degree of 1 up in my numerator. And I got to be careful down here. If I FOILed these out, what degree would those multiply to? Those would be quadratic. So I'm going to have a horizontal asymptote. Since m is less than n, horizontal asymptote is y equals 0. Head to your x-axis, there's your last asymptote. And there we go. Now we're ready to graph. So we'll head back to the calculator. We'll just get a shape of what this is looking like, and then we will sketch it out. So we'll head into here, and we'll put in our numerator. We're going to have a x plus 6. Denominator, x minus 2. X plus 3. And hit your graph. So there's our shape. So we're seeing our x minus 3 vertical asymptote, our x plus 2 vertical asymptote, and then our y equals 0 horizontal asymptote. Again, I'm just going to sketch it. You can head to your table if you want to find a couple of points. They're not going to be pretty, but they'll do the trick if you want to do it that way. But I am just looking for sketches. So we can kind of see following my asymptote, it's kind of coming up and then turning, coming back down. We've got a hyperbola following this asymptote, and we've got a hyperbola following those asymptotes. So there would be our picture of that function. We can see when you do the work ahead of time, you get all your asymptotes laid out, then the sketch, goes pretty simply. Just put that all together. Heading on to D. So D, we'll get everything factored. Here's our first one we've had to factor. So it's a basic trinomial. So we look at what multiplies to 9, adds to 6. That's going to be x plus 3. And another x plus 3. Down our denominator, we also had an x plus 3. And check your point of discontinuity. Our point of discontinuity is negative 3, but it does remove with one of these up here. So if it's removable, am I going to have a vertical asymptote or a hole? You can ask yourself. That's going to be a hole. So here we're going to have a hole at negative 3. Okay, so we're going to graph that in. Again, I don't know where the hole is. Asymptotes I could graph right away because I know that along this whole negative 3 it's not working. But since this one is now going to take the shape of a linear, y equals x plus 3, I have to put negative 3 in to see where the hole is. But here's going to be the graph shape right here. So we did one like this on part A. If things start to simplify and remove, whatever's left, that's going to be the shape of your graph. So this one's just a slope-intercept form, 1x plus 3. Okay, now to find what happens with this hole, we're going to put negative 3 in. So that would be negative 3 plus 3, which is equal to 0. So now I know my hole is at negative 3 0. So asymptotes, you can just go ahead and plot those out. You know exactly what's going to happen with an asymptote. Whole, we do have to use the remaining, what's left of the function, figure out where is my whole going to be located. So -3, 0, we'll graph that right here. There's going to be your whole. And then we'll just graph our slope-intercept form. So y equals x plus 3 is a y-intercept of 3 and a slope of 1. Try this here. And there would be our line. I don't like that. Let's do it like that. And heading off that direction. So at just some point, where that hole is, you got to just make a little bit bigger circle, open circle, so that you know where that is. Are you guys seeing me again? All right. So I'm going to cut it off right there. Thanks for joining. I'm going to post this. It takes a little bit of time to load the video to YouTube, but it'll be posted over the weekend. You can take a look. You guys are doing awesome. I can't imagine doing, like, what are you guys doing, 6, 7 online classes right now? So keep it up. You're doing awesome. And we will continue next week, finishing up chapter 8. And then I think we're going to have a test on April 21st. So we're just going to keep following the same plan. How do you guys like the pacing of it? Like one lesson every 2 days? Good?
Yeah.
Yep. So we'll keep that going in the next chapter. So we'll start looking at trig. We'll finish up the year with chapter 13. You guys are probably watching the news. I don't know what's going to happen. Right now, I'm just assuming that we're going to get ready for online learning in May, but hopefully we're back. But I just think you guys are doing really well, doing awesome. Proud of you. So keep it up. All right. So I will post this, look for it on an update, and then I'll also put it in the materials so that you can find it in there as well. Okay, thanks for joining. I'm going to end the presentation. We'll see you later. Good to see you.